Hello everyone, welcome to this presentation where we are going to talk about how to use Amaranth to manage the material available in your FPGA. To start, we'll go over some details about how synthesis works in general for FPGAs, and then we'll see how Amaranth handles this to provide us a simple way to access resources of your board. And finally, we'll see how to instantiate a PLL, which is quite a particular kind of resource. It will all be demonstrated on the latest ICE4E UP5K board. So now let's see a bit more about FPGA synthesis. Currently, there are many different kinds of FPGA. Some are quite cheap, others have a lot of features but their price may grow up quickly. What's most important to remember is that there are plenty of different boards providers, which is a shame because each provider uses a different synthesis placement or routing toolchain. And sometimes even one constructor uses different toolchains for different series. In fact, the only thing they seem to share across this electronical ecosystem is the hardware description language. So that's where the HDL here comes from. And you need to know that most of them use Verilog. This low portability can be seen through this quite simplistic diagram. For Xilinx platforms, such as the ZC706, the board logic description should be written in Verilog, and the toolchain we use is Vivado. This toolchain also needs a .xdc file, which will tell the software about the characteristics of your board. As output, you get a .bit file, which is something you directly flash onto your board, and then you're ready to go. For latest ICE4E boards, which is cheaper, you'll need some open source softwares which separately execute the synthesis operation, the placement and routing operations with NextPioneer and the packer to finally adapt the LUTs and flip-flops to your ICE4E board. However, you don't need the same constraint file required by NextPioneer, and you won't get the same bitstream format neither. But if you're using another kind of platform, let's say a Cyclone 2, well, you'll need to install Quartus to generate your bitstream, but this bitstream will still not be in the same format as the previous one. And even if you use the vendor tool to convert your bitstream, well, different formats again. And I won't talk about any other toolchain, this would almost be as pointless as trying to list the asteroids in the solar system. So, is that it? New FPGA board mean new software, new files, new bugs and all? Well, not exactly, because Amaranth is there for you. If you have seen the previous videos on the subject, you could see that this hardware description language is quite simple to manipulate. It is generating Verilog files that could be used if you wanted to execute synthesis, placement and routing manually, but it also manages the toolchains so that you don't even need to care about this. Just focus on the programs of your FPGA description. But I'm hearing someone from the back saying that every board is different and not all of them are using the same inputs and outputs for FPGAs or DAC or SMA ports. Well, you're right. And that's why you should look at the Amaranth list of constraint files. Unlike the diagram I showed earlier, they all have the same format and you should refer to them to use the resources they describe. So let's see that. You'll find them in the Amaranth boards directory. Each platform description file contains a description of a Python class which has at least 4 properties: device, default clock, resources, and connectors. Device is the name of your platform. You can use it to know on which platform you are flashing your program, and so it allows you to describe in your code different implementations for different boards, but with the same behavior in the end. The default clock is how you get the information of what clock is used on your FPGA. Resources is a list of all the materials you have on your platform, and so this is all the thing you can access very easily thanks to Amaranth. And finally, the connectors is the list of generic connectors available on your platform. So within the elaborate method we describe in every module we are writing with Amaranth, you could have seen that there was a parameter in the previous video called platform, which we never used. Well, that's because we were only working on simulations, but now we are talking about actual material. We will make use of this platform to check if a platform is connected at first, and then once we have checked if the platform is connected, we can also check what kind of platform this is through the platform device attribute. And if we know which device we are using, we can refer to the description file of the platform we are using to know what are the resources we can request. And the request method of the platform class allows you to create new signals, like my resource here, which you can use just as regular signals. So if your resource is an input resource, you can use myResource.I to say, for example, that we want a signal to change every time we switch a button. And so if we request a switch button, we just use myResource.I as the input of this switch button. And we can do the same with output. For example, let's say we have LEDs on our platform. Well, we can use myResource.o to switch on and off the LED by saying that myResource.o dot equals anything within the combinatorial or synchronous domains. But one thing that is interesting is that you can also create your own definition of a resource and add it to the platform you are using. And to do so, you can use the method addResources to describe a new resource. So it takes the form of a name, an index, and a sublist of signals which describe the inputs or outputs you wish to use for your resource. So let's say, for example, you want to describe an interface with an input and an output in particular. If you know on which connector they are for your platform, you can describe the pins within the subsignals. And in the end, you can consider that these platforms contains a new resource called IORS, which you can request just as before to use IOResource.input and IOResource.output to input and output things within this new resource you've created. So for now, let's try this to implement the pseudo-random noise generator we described in one of the first videos of this series on this ICE40 UP5K. To start, we are going to import what we need to implement our program. So, as I said, we are going to implement the linear feedback shift register with some connectors to make sure we can output the signals we calculate on the GPIOs of our FPGA. So we need to import Amaranth, of course. We won't need the simulation module this time. We import the prescaler and we import the functions from PRN generator. So the prescaler has been explained in the video about binary phase shift keying modulation, BPSK. You can look for it on the web if you haven't seen it yet. And the PRN generator is what we implemented in the video about linear feedback shift registers. So we are going to use these different modules to create our connector class. So in this connector, we are going to first of all define the elaborate method as usual and the module. Alright. From now on, we need our PRN generator module, so m.submodules.prn equals PRN generator with parameters 8 for the size, 43 for the taps, and 1 for the seed. And now we can check on which platform we are working. So if a platform is connected, we can also check if this platform is the one we intend to work with. So as I told you before, we can use the device attribute of our platform to see if that's the right platform. So to know what is the exact name of the device, you can look at the file that describes your board. So for my case, this is the file inside the Amaranth boards module called ICE40 UP5KB evn.py. And when I look at this file, so I see that the device is defined with this name. I can also take a look at the resources I'm able to use for my program. And that's exactly what we are going to do here. So as the PRN submodule is already defined, we just need to define inputs and outputs for it. In fact, instead of just doing a request on the different resource we have, we won't output our PRN on any LED or a classical resource like the SPI flash resource or anything. We are going to use the connectors. Let's say I want to use the header B J2 connector. Then the connector I'm going to use is J1. So I define a tuple with J1 here. And let's say I want three different subsignals for the resource I'm going to create on my platform. I want to use a pin as output for my PRN, another pin as output for my clock signal, and another pin as enable signal, which will be an input pin. I use the platform.addResource method. So when you add resources, you always do it with an array, and we will use as resource something we'll call linear feedback shift register. We will give it an index of 0, and let's define the subsignals. So I said the first one would be the PRN, so let's say it is called PRN. The pins I'm going to use is the pin 7. So 7 means that I'm taking not the first, the second, third, fourth, fifth, sixth, 7. So by saying I'm using pin 7, in fact I refer to this one, the number 26 here. So the connector I'm going to use is the J1, so I can just say connector equals con, and the direction of this pin will be an output pin, so I say O right here, and we can just do the same for other signals. The second one, we'll call it clock. Let's take the number 11. So here if J1 is 26, so it's 7, 8, 9, 10, 11. We take the pin 32. Connector is the same, the direction is the same, and for the input, which will be an enable signal, so we'll call it enable. Here, let's say we take 15. And the direction is input. And to finish with this, we also need to specify what kind of connection we are using for this resource. And we can see that here we are using sb.lvcmos, sb.lvcmos. So we can suppose that, in fact, all the connectors are using this IO standard too. So here IO standard equals sb underscore lvcmos. And we add this as an attribute. So now here we close the resource, and then we close the array and then the call to the method. And we are done for describing the pin of our device. We can request this resource we described. So we say that we'll call it interface. And we request the resource that is called linear feedback shift register with the index 0. With the index 0. We define the prescaler to set the speed at which we will output the PRN. The input frequency of our prescaler will be the platform default clock. And the frequency we wish to have as output will be, for example, 2.5 megahertz. Then we define new rules. So it will be a combinatorial set of rules. We can call interface just as described earlier, so interface.prn, which is an output signal, prn.equals, and we use prn, which is here our submodule, dot output. Interface.clock, which is also an output, will be clock signal. So this is the speed at which our FPGA is calculating. And we use the synchronous domain clock. And we set the prescaler enable equal to the interface enable, which is an input signal. So now we kind of plugged all the things we need from our device to the different GPIOs. And the last thing we need to do is to make the PRN shift. And so we can just say that the shift signal is equal to the output of the prescaler. And we should be good. You can remark that if we wanted to, we could have defined a resource with the same name, but for another platform. So let's say I want to do the same for ZC706 from Xilinx. Well, I can just write this. So here is the name of the device I'm using, following what I could have read on the platform description. Here is the connector I decide to use. Here is the name of the resource, so it is also called linear feedback shift register and 0, so that in fact, even though I'm not using the same platform, because I described the resource with the same name, I can refer to it outside of my else condition to 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 input and output everything the same way as I did for the other platform. So we return the module and we're done. Let's run this. Let's run explain material. So apparently I forgot a comma here. We also forgot one detail, it's that if we wish to flash it on the board, we need to define a main method. So the board I'm using is the ICE40 UP5KB EVN. So in fact I'm just importing this file we described before. And we will need to use the .build method, and the parameters of it are the name of the module we wish to connect to flash inside our board. So it's connector, and we set the attribute do program to true. And now if we run the script again, we can try running it again, and you see that everything is flashing. Okay, so let's see what it looks like on the oscillator. Alright, so here is our setup. We have an oscilloscope right here, which is reading the output of this, and here we have our latest ICE40 UP5K board with the pins we decided to use, which are on J2 here, header B, and so the pins are displayed as this one, as this. Here you have output 1, 2, 3, 4, 5, 6, 7. 7 is where we decided to put our pseudo-random noise. So let's see what it looks like when we plug it here. On the oscilloscope, we get a nice noise. If we just run a single time, we see this. So now the question is the frequency of the pseudo-random noise equal to 2.5 megahertz, just as intended? To do so, we just read here to see if the frequency is right. Oh no, this wasn't the smallest interval you could have. The smallest interval you could have is here. The oscilloscope tells us that we have 2.4 megahertz signal for the frequency at which the PRN is changing. So it appears to be well. Let's look now at the FPGA clock. It should be a 12 megahertz signal. So here we have signal 1, 2, 3, 4, pin 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's where we put the clock. And now if we run this, we get this kind of signal. So the question now is, what is the frequency of this signal, and it seems to be 12 megahertz. So it's alright. Now we can test the last thing about what we did earlier. It's the enable signal. So let's look again at the PRN, and when the PRN is being run continuously, we see this kind of waveform. And I'm using here this little wire to say to the enable signal if we want to enable or not our output. So this was a PRN clock. So here is where we are inputting the enable signal, and so you see that currently this is working, and I should plug the ground because this is by default, this is active high. So now we are going to say up, and here when I'm unplugging the ground to this input, we have the PRN, and when I'm plugging it, there is no more signal. So the enable signal seems to be fine too. Using GPIOs is fine, but you may also be interested in seeing how to use different materials that are not represented in the Amaranth board description file. A good example would be to see how to change our FPGA clock rates with a PLL. To make it as simple to understand as possible, a phase-locked loop, or PLL, could be summed up by this diagram. We have an input signal with an FREF frequency, and it's about to be filtered to be the input of a voltage-controlled oscillator here. We then use this VCO output both as the output signal and as a retroactive information that is serving our PLL. You see there and there that within the PLL we operate a multiplication and a division. These are the parameters we control to choose what frequency to output. You'll have the occasion to see what it looks like in Amaranth within the next minutes. So let's implement this. But before we dive in, note that I'm about to program on a Lattice ICE40 UP5K board. And because we are talking about material, the Amaranth instantiation may vary from one board to the other. In fact, it's very likely to be the case. Some boards require to use buffers before and after the PLL to use its signal. Some will need to use different PLLs following where the signals you wish to use are coming from. You see, it still depends on the board you're using, despite the fact Amaranth tries to unify the practices of FPGA. So, implementation time. If we want to change the clock rate of our FPGA by using a PLL, first of all, we need to define a different clock domain for our synchronous operations. So we say m.d domains.sync equals a new clock domain. Alright, we say it has no reset because it will be defined by the output of the PLL. Then an operation which is specific to the Lattice ICE40 platform is that we use the platform lookup operation. If you're working on another platform, it may be different. Here, the input clock will be the clock we'll use as input for our PLL, and as I showed in this file, which describes the board on which I'm working, the default clock is currently clock 12, and it is defined as a resource that I can directly request here with the name clock 12 and the index 0. Once I requested this input clock, I can define some signals that are required for my PLL. The PLL will be described in a submodule, and as this is not something we describe neither in a file elsewhere nor in the description of the platform here, we need to create something that Amaranth calls an instance. An instance is just a generic object that is used to describe stuff. Everything I write in my instance can directly be translated from Amaranth and Python to Verilog code. So in fact, you need to know the Verilog code for using your PLL in order to instantiate correctly your PLL within Amaranth. Here I give the name of the module I would be describing in Verilog. So in my case, this is SBPLL 40 pad. And now I'm going to describe every parameter of this PLL. So in Amaranth, when you want to say that the code you will translate in an instance as a parameter for your module in Verilog, you need to put the prefix p underscore. So there is a parameter called feedback path. So I write p underscore feedback path, and the attribute here should be equal to simple. There is a total of 5 parameters, so I will go over them and their explanations later. So here I'm done with the parameters for this Verilog module described in the Amaranth instance. Here you find some parameters that in fact are related directly to the way the PLL works. Here you see that we have a multiplication and a division. Well, those operations are related to these parameters. At first, we know that here the clock was a 12 megahertz clock, and if we wish to have, for example, a 100 megahertz signal as a clock for our FPGA, then let's look at the datasheet of the ICE40 UP5K platform. So here you see the different parameters I'm giving in the Amaranth instance, and what I'm looking for is this formula. So in fact it's this one here. You see that the output of the PLL is equal to the input of the clock, so it will be the one we give the one we plug inside our instance, and the div_f factor here in fact is div_f plus 1 multiplied by the original clock. So I wrote in the program that div_f was 66, so in fact we make the operation 12 multiplied by 67 and then divided by 2 to the power 3. So 2 to the power 3 is 8. If you make the calculation, this gives us 12 multiplied by 67 and then divide by 8 is like almost 100. So this is the right parameter. These are the parameters to create a frequency of 100 megahertz on our FPGA. Let's keep going on. So now that we defined the parameter of our submodule, we need to define the inputs and outputs. So as output we have the log signal, which is equal to something we'll describe right here. Let's describe a new signal called lock. And so when the PLL is locked onto the frequency we asked it to give out, then this signal will be equal to 1. So this is an output of our submodule. And as input we have a reset. We'll set it to 1 because this is an active low signal. There is a bypass signal which is active high. So if we want to get rid of our PLL, we just set this to 1. Then we have the package pin, it equals the input clock. So this is a specificity of the PLL I'm using. In fact, this is the reference clock. it's called the package pin here for some reason I will not explain, as we would be going too deep into the subject. And then as output we have o.pll out core, which is equal to a new signal we'll call PLL out. And we're done for the description of this instance. So now, if we want to set the output of the PLL as our clock signal for the synchronous domain, we simply say that m.d.combinatory domain receives the new rule that the clock signal sync will be equal to the PLL out signal. And we are done for this. So let's check it out. I forgot commas all along the way. So here you see that when you put a P as a prefix, it means that this is going to be a parameter for your submodule inside your Verilog program. If you prefix with an O underscore, that means this will be an output of your Verilog program. And if you put a prefix which is I underscore, then this is an input for your module. Here, this is not ATTR, it's ATTRS. And now this is flashing again. And hopefully the frequency we will see is 100 megahertz instead of just 12 when we look at the clock signal. So let's see that on the oscillator. Okay, so same setup as before, but now we have used the different clock which is modulated by the PLL. So we can look here at where we have the output of the clock, which is on this pin. And when we look at the oscilloscope, we can read the frequency of our signal. Okay, so let's see how long is one period. And we can see that the frequency here is around 100 megahertz, so the PLL is working well. During this presentation, you had the occasion to see what an Amaranth platform constraint file looks like. You have learned how to access GPIOs described in such files, and you could probably do the same for other resources described in the constraint file. And finally, you learned how to access and use a PLL to change the clock rate of your FPGA with Amaranth. Thanks for watching and have a good day.